constraints, security things. And if you talk about the resiliency, circuit and system resiliency, reliability is equally important. Okay. So yeah, a few things we touched in the last lecture, like we try to understand what is the VTIA, how it happens, and how it can impact the performances of devices. But let us try to understand all major reliability issues. And for any kind of system, whether it is the AI hardware or any kind of SoC you are making, maintaining the reliability of the chip is equally important. So yes, so security and reliability both are important thing. And that was one of the motivation to keep my lab name like IC Rescue, like reliability, security, because I have already completed yesterday, so I have removed from here. Reliability, security, and quality. So today we will be discussing about reliability and quality, and security we have already finished. Okay, so rescue will be done today. Perfect. So I will be talking about different kind of the reliability issues, and we'll try to see what are the reason and how this kind of reliability issues comes, and what are the possible solutions to overcome those problems. And at the end, I will also try to explain if you are interested in doing research in reliability, what are the scope, near-term and the long-term research plans, and where you can think of like that is start from the devices to systems or to architecture. So, and the impact of any kind of reliability issue is different at each abstraction level. Okay, so we'll discuss all those things. I have 31 slides, so I need to finish in 1.5 hours. So fine, perfect. So this will be the content that I will be covering, like from technology scaling, then various reliability issues. That is start from the PVT variations, VTI we have already covered. Then I will talk about SCI. We'll say like how this SCI is different from the VTI. Ultimately, impact is remain same. And then we'll talk about time-dependent dielectric breakdown. This is one of the serious concerns, especially at the scale technology, because the whatever the interconnection, other things which we are using, or oxide thickness we have, it's very small. And a small wear and tear may impact the performance, or that can break the device, and ultimately your whole system can be broken down. So maintaining the time-dependent dielectric breakdown and see the impact is really very important. And ultimately, then at the end, we'll talk about combinedly what is the impact of all these things. Okay, and then at the end, I will tell you like, if I'm talking about any reliability concern at each abstraction level, how that matters, how they are impacting, and which of the parameter is changed at the device level, at the circuit level, or at the system level, or at the architecture level. And then one more important thing, like especially if you are making your chip for space applications or harsh environments, the soft error becomes equally important, because this is radiation kind of things. So radiation hardening, maintaining the hardening against the radiation or high energy particle is also important. So we'll talk about how they can impact the performances of devices, and how that can change the logic in combinational as well as in the sequential circuits. And then at the end, I will try to explain what are the different reliability challenges in near term and in the long term plans, and where you can think of if you are planning your research in the reliability side. Okay, so with this brief introduction, let us start with the basic thing, this is really very important diagram. If you see, this is a very recent publication, like 2022, and they summarized most of the technologies and how the scaling happens, and if scaling is happening, how they are different from each other, and what are the different kind of verticals that you can think of. Okay, so if you see, like before 90 nanometer, we can call them the happy scaling era, because whatever the size of device you have, simply scale down all the dimensions, whether it is length, width, thickness, whatever it is, simply it was behaving like whatever you was expecting. But This is not true after certain technology nodes, and that technology we can call them the like 90 nanometer. So in that case, if you want to maintain the similar kind of performances, like Moore's law says that your performance should increase, area should reduce, and all these things, you all know that thing. I'm not going to explain what is the Moore's law. But if I want to maintain that Moore's law for the performances, for power, and for area and other things, definitely we have to see like whether my new device which I have scaled down is working like that or not. Okay, so in that case, the previously I just told you, up to certain technologies, simply syncing the devices or scaling down the devices, you can achieve those parameters, those performance parameters. But beyond certain technologies, it is a bit difficult. Okay, so it's not just simply reducing the size of the devices like width, length, oxide thickness, and whatever you have. In that case, you have to think about, can we have a different kind of material that can help to maintain the performance which I was expecting at the lower technology. So those kind of technologies like that, we can call them the material-based scaling era. So it's not just the physical reduction of the devices, but also the utilization of different kind of materials so that that material can help to maintain the performance which I want. Okay, so this kind of scaling era we can call them. Yeah, so then high K material and then FinFET based structure, they came into the picture and they were able to maintain the performances like whatever you was expecting. So in reality, if we talk about the size, the physical size was not actually scaled down. After that, actually the performance based understanding was important. Like you have to see the performances. I don't care about what area you need. Maybe if you are fabricating the FinFET, might be that can require more area than the older technology because they have more number of fins. Okay, so there are many things that comes into the picture. So until certain technologies like 5 nanometer, the FinFET was there. And then there are more things like if you want to use for a certain applications, like there are more verticals, more than Moore's law, photonics IC, neuromorphic computing, quantum technologies, and the 2D material-based devices are some of the verticals that people can explore. It depends what kind of, what is your applications, how you want to deal with, and accordingly you have to explore the dimension where you want to do. Like especially photonics, like if you want to achieve high speed, then you know that photons have the higher speed than the normal particles like electron and holes. So definitely for high performance applications, photonic could be one of the future where you can achieve high. So you know that the Moore's law says that we are able to get many things good, like power and other things, but getting the same kind of frequency trend is a bit difficult. You are not able to get the similar kind of frequency. So this could be one of the way like you can achieve the similar kind of operating frequency by utilizing the different kind of technologies like photonics IC. Okay, then neuromorphic computing, like this is just an analogy of your brain, something like that. So if you are thinking to like, and he will be speaking about these things in more detail. And then the quantum technology, yes, because there is always a limit of scaling down, because what happens after 1 nanometer or 2 nanometer? So you cannot keep reducing everything, right? You need certain dimensions. So then after, the new kind of technology will come into the picture, and that technology we can call them the quantum technologies. Similarly, yeah, more than Moore's, like if you are thinking of something like MEMS kind of devices, so those comes under the more than Moore's kind of technology. So there are a lot of technology. It depends what is your applications, where you want to like what is and what you want to design, what is your requirement in terms of frequency, what is your requirement in terms of power budget. So accordingly, you can pick a particular technology. It's not like you have to always pick a quantum technology. No, that's not required. If your application is very low frequency, like biomedical application, there you don't need high performance. Okay, you need a low power. Okay, so in that case, what is the role of quantum computing? Someone may say, okay, I will develop this thing with the help of quantum computing for biomedical application. This is completely ridiculous. You cannot do that. You have to decide what is your application, and accordingly you can select the technology. Is it fast or is fine? Okay, because I have 30 slides, so I am speaking a bit faster so that I can deliver all the content which I have, right? Okay. Otherwise, I have to reduce the speed of my speaking. Fine. Perfect. So I think we understood like what are the different technologies, what is the importance of those things, and how to pick a particular technology based on my requirement, based on my. Okay. Now, if this is the simple thing which everyone knows, like scaling down. There are two kind of scaling, like the constant field and the constant voltage scaling, and you know that how it could happen. And definitely in each next technology generation, the oxide thickness is reduced by 30%. Now here is the question: if the oxide thickness in each next technology generation is reducing by 30%, definitely reliability is important here. Okay. So with these technologies, the reliability and the variability issues play a major role. They start dominating the performances, and then we have to take care how to maintain the reliability, how to get better reliable circuits, or how we can avoid, how I can make the process tolerant, like process variation tolerant circuits, or any reliable circuits. So here is the like, especially at the scale technology or at the lower technology, the reliability becomes challenging, and the critical parameter that need to be investigated, that need to be checked before fabricating the chips. Okay, so so if you talk about, there are two major things. One is the excessive leakage power, because if you scale down the technology, definitely the power becomes one of the constraints, one of the problem. And the second one is the reliability. So these are the major things that need to be addressed at the scale technology or at the lower technologies. And other than these things, I was talking about, yes, the PVT variations. One more thing that I have already told you, so whatever like process voltage and temperature variation we are talking about, these variations are with respect to, like, at any point of time it can happen. Like at the time of fabrications, process variation can happen. But yesterday I was talking about, there are two kind of reliability concern. One is a time zero and one is the time dependent one, or that we can call them the temporal degradations. What is the difference between these two? The major difference between these two are, if I'm talking about the time zero variabilities, time zero reliability concerns, in that case, they are independent of time. Okay. But if we talk about the temporal degradations or time dependent degradations, definitely their impact increases with respect to time, like NBTI. The NBTI effects or SCI or time dependent dielectric breakdown, these are some of the reliability concerns where impact of these reliability issues keep increasing with respect to time. At the time of fabrication, there is a less effect of these things, or ultimately no effect of these things. Okay, so they happens. So this kind of reliability issues, we can call them the temporal degradations, and here they are listed. Okay, BTI, SCI, and the time dependent dielectric breakdown. Other than this, there may be one more reliability concern that need to be considered or that need to be addressed, and that reliability concern we are talking about, and that is the soft error or radiation hardened circuits. From where this reliability concern comes? This reliability concern is especially important, especially if you are trying to design your chip for the mission critical applications like space, where the probability of high energy particle is too high, and might be this high energy particle can strike into your sensitive node in the circuit, and they can trigger, they can generate an impulse, and might be your logic can flip, especially in the memory elements. Okay, so here you have to think about how I can design my circuit so that it should be soft error tolerant. There are various factors that decides to make any circuit like a reliable, like soft error tolerant, but the critical charge is one of the parameters that decides how reliable your circuit is and how to check that one. You cannot simply calculate the critical charge. Definitely for each high energy particle, you must have certain soft error rate calculation as well. So there are many factors need to be calculated. It's not just increasing the critical charge. Okay, so maybe you can go through some of my paper where we have listed those parameters. Recently, two review paper we have published on this radiation hardening side. Aryan has published those papers. And from there, you can get the idea like what are the different energy levels, what should be the critical charge, and if I have a different kind of high energy particles like proton source or alpha particles or neutron, whatever it is, for that how much energy how much energy they require, and what should be the minimum critical charge so that I can sustain those high energy particles. So those are all are listed in that paper. You can go through it. Okay, so with this, like we understood what are the different kind of reliability issues, and let us try to understand one by one. If you have any question, you can ask in between. Okay, so online participants as well, you can ask the questions if you have anything. You can write in the chat box. The people are monitoring it. I will answer those things immediately. Okay, so yeah, I think this is what I have already explained in the last lecture. 3 ages of resiliency. And in resiliency, if we talk about, there are two things, reliability as well as the security. So security we discussed in the last lecture. Last 2 lectures, we have already taken 4 hours of lecture in security. Now, we'll be talking about the reliability part, some of the reliability part like PBT variations, NBTI, SCI, TDDB, and soft error. So we'll be discussing about all those things. So this is the second part of this resiliency that we can call them from CAS resiliency. Okay, yeah, these are some of the reliability mechanisms, reliability failure mechanisms or reliability concerns. They are divided into 2 things like time zero and time dependent, which I was discussing just before, like in the first slide only. So time zero means like which are independent of time, and time dependent means with respect to time, the kind of reliability concerns are happening. Okay, so generally like BTI, SCI, TDDB, electromigration, these all are the time dependent one. Definitely, the software is also one kind of time dependent because at which time, like the impact of high energy particle will be more, it depends like where you have put your circuits. It's not like at the time zero only it will happen. No, it can happen at any point of time. Similarly, if you talk about the time zero or the local and global one, we can call them the intra and inter-die process variations. And all these are RDF, LER, all these I will discuss you, like discuss with you what these reliability concerns are and what are the main source of these problems. Okay, yeah, so let us talk about is it fine? I'm connected with you or not? I don't know. If you have any concern, definitely you can ask the question. Okay. The talk should be well connected. Huh? Otherwise, one-way communication is not good. Huh? Okay. And that will only happen once you will ask the questions. Huh? So that I will understand, okay, you are listening my talk. Otherwise, you had a great tea and then you can sleep. Huh? In open eye, right? That is also possible. Huh? Okay. Good. So let us try to understand what the process variations are. Basically, they are classified into 2 categories. One is the global variation and the second one is the local variation. The global variation is like, yeah. So if you see, like, let us assume, you know that what is the wafer, right? So from a single lot, you can cut the n number of wafers. So if the variation is like, if I have sliced 2 wafer from the single lot, it is not possible. Yeah, there may be possibility that both the wafer have different kind of property. It is not true that both the wafer will remain same. Okay, so this kind of variation, you can call them the wafer to wafer variation. If you have a 2 lots, like you have got 2 ingots, might be these 2 ingots could have a different kind of property. That's also one of the possibilities. So you can call them the lot to lot variation. Similarly, wafer to wafer is done. On a single wafer, there could be multiple dia. Okay, so if even though you have replicated them, you want to both to be the same, but still there are some variations in those dia. So you can call them the dia to dia variation. Okay, and even though in a single dia, if you have designed a similar kind of circuit twice or thrice, maybe each circuit will perform differently because of this process variation. So this kind of variations, we can call them the intra-die variations. So intra-die variations, like they are uncontrollable, and at the time of designing, you need to have some margin, even though there is some variations, whether my circuit is working properly or not. If it is working, then these variations are acceptable. But the only thing is, if they are beyond your limit, beyond your whatever set boundary you have decided, then you cannot say this is the reliable circuit. Okay, so of course you cannot remove 100% variations. Okay, but there is some threshold, there is some range. Up to that range, your circuit will work properly, because, and that is being tested by the Monte Carlo simulation. You can test from there. Okay, Monte Carlo simulation is a great tool that help us to give a prediction of range, like what is the range of a particular parameter distribution and what is the mean value, and accordingly you can see what is the range up to which I can operate my circuit. And if that range is within your requirements, definitely your circuit will work for all the ranges, whatever you want to do. Okay, but if it is crossing that window, that's the problem. Then you have to check the circuit, you have to redesign it so that you can maintain that one. Other than these things, I think everyone knows different process corners. They are especially important. Like major parameters, if you talk about for any circuit, is the power and the delay. Okay, and all these process corners that gives you certain information. What that information is, if you see like this fast process corner, that simply indicates that the threshold voltage of PMOS and NMOS transistors are low, less VTH. Okay, if you talk about the slow process corners, the threshold voltage of both the devices are high. And if you see the typical, they are in between. Fast slow, it means that one of the threshold voltage is high and one of the threshold voltage is low, and the slow fast is the different thing. Now, what is the use of these process corners? There could be other four corners as well. What those corners could be? One could be the typical one could be the fast, one could be the fast and typical, and so on. So you can come up with the other possible combinations as well. It is not about the slow, fast, slow, slow, and fast, and typical. You can keep one transistor at the typical, and the second one could be the slow or fast. So there could be other possible combinations as well. You can check it out. But yes, because they are within the boundary, so they may not be required because they are the extreme conditions. If you have checked your circuit at the fast and the slow, if they are working well, there is no need to check at the typical. Okay. So now the question is, there are two parameters that need to be investigated. One parameter is the reliability, and the second parameter is the security. One parameter is the power efficiency, and the second parameter is the delay or the performances. Now, we know that we have already studied before, like the threshold voltage is one of the parameters that decides what will be the power dissipation. If you have the higher threshold voltage, power dissipation will be low, but the delay will be higher. Okay, so this is what you know. So this this fast and the slow corners gives you the information about the power and the delay. Let us assume I want to design a chip, okay, or any circuit, and I know that my power budget is, let us assume 10 nanowatt to 12 nanowatt. Okay, so let us assume my maximum power budget is 10 nanowatt to 12 nanowatt. Okay, so now this is my range. Beyond that, I'm not expecting my chips to dissipate more than 12 nanowatt. Okay, now I know that if I'm considering the fast, okay, so in that case, both the threshold transistor of both the threshold voltage of both the transistors are low. If the threshold voltage of both transistors are low, they will dissipate higher power. Okay, so if I'm operating my circuit at the fast process corner and I'm getting some power, and if that power which you are getting is within your window, it means that even after operating at fast process corner, my power budget is within my window. It means that I have designed a good chip. So basically, the fast process corner gives you the information about your power specification. That check the power specification, whatever you have, accordingly you can understand, okay, at this process corner, if I am getting power dissipation within my specified range, then it means that if I have more threshold voltage than this one, definitely that will receive less power. Okay, so maximum power dissipation will be at the fast only. And if it is within the window, there is no problem at all in the circuit. Similarly, if you talk about the delay, at the slow process corner, because you have a higher threshold voltage, definitely delay will be higher. Okay, if the delay is higher, what does it mean? If, let us assume this in the similar way, if you have decided like the speed or the delay of my circuit, like the acceptable range of delay, let us assume 10 nanosecond to 12 nanosecond is the range. Like this is what your range is. And even at the slow process corner, if your delay is within that window, it means that you have designed good circuit, because even at the extreme case, I am getting the less delay or the delay which we have decided. So the slow process corners gives you the information about the delay specifications. But it is not true that at the time of fabrication, let us assume if I have a PMOS transistor and NMOS transistor, both threshold voltage of both the transistors will be higher or threshold voltage of both transistors will be lower. There may be possible one of the threshold voltage will be higher, one will be lower. So other than like for that purpose, you have to check like how my circuit is behaving if I will consider the slow fast and the fast slow process corner. So there are other possibilities. You can check your circuit performances at other corners as well, but more important corners are the slow and the fast process corners. If your circuit is working well in terms of delay and the power, that's perfectly fine. Yeah.
The slow fast and the slow corner, I'm seeing like the threshold voltage of NMOS in the case of slow.
This is just the analogy. Yeah, it could be like here as well.
It could be a perfect rectangle.
Yeah, that's also possible. It could be perfect rectangle. This is just to make like this is possible. So see, yeah, very good question. Let me extend your question. Okay. So what can happen? Let us assume if I am designing a circuit and let us assume the minimum threshold, the typical threshold voltage is let us assume 0.4 volt. Okay. And the minimum threshold voltage may be 0.3 volt and the maximum which I am getting is like 0.5 volt. So here I have a range like 0.3 to 0.5 and typically 0.4. There is a possibility I can, like some other transistor will have a threshold voltage of 0.35. So that's also possible. So this is how it defined, like whether it will be diamond shape or it will be rectangle shape. So it depends, like, yeah, so it's kind of window. So extreme one is a window, in between there could be any value. Okay, so this is what the corner says and how it works. Now, yeah, I was talking about some of the local variations, and those local variations are like oxide thickness variation. Now, what this oxide thickness variation is, I have already discussed at the beginning that with each technology generation, with each new technology, the oxide thickness is keep reducing by approximately 30%. Okay, this is what we have seen in the first slide. Okay, now what is the impact of this reduction? The impact of this reduction is, let us assume initially I had some thickness of your oxide, might be in the next technology your thickness has been reduced. But to get that oxide thickness, you are doing the oxidation process. Okay, but is it possible that you can create a uniform oxide on top of the silicon? That may not be true. Okay, so you are expecting that the thickness of your oxide should be 2 nanometer for entire bulk or entire silicon substrate, whatever you have, but maybe there could be some variation. Some variation may be possible. Okay, might be the thickness at some point may be higher than what you are expecting, and at some other point it may be lower than what you are expecting. Okay, so this kind of variations, you can call them the oxide thickness variation. Now let me give you some numerical understanding about this variation and their impact. Let us assume I have older technology. Okay, in older technology, my oxide thickness I am expecting is like 5 nanometer. Okay, and there is a possibility of plus minus 10% variation. So 10% variation tells us like my thickness could be 4.5 nanometer to 5.5 nanometer. Okay, so this much of variation you have. Now, so this is one of the things. Or second, in other way I can say, if my oxide thickness is 5 nanometer and there is a possibility of variation of 1 nanometer or 0.5 nanometer. So the range will be 4.5 to 5.5. Now, again, I am considering the new technology where my thickness is 2 nanometer. Oxide thickness which I am expecting is 2 nanometer. And again, the range of variation is 0.5 nanometer. Okay, so again, my range of variation is 0.5 nanometer. Now, my thickness will be 1.5 to 2.5. And if you see the percentage, that will be more than 25. So even though the amount of variation is remain same, but because your oxide thickness is reduced, the impact of that variation is more at the lower technology. And this is what we call the oxide thickness variation. And this is what I'm saying here. This is really very important thing to understand. Like at the lower technology, they are more probabilistic because you are considering the lower oxide thickness, and the amount of variation is even though remains same, but the impact is more. Okay, so this is what we can call them the oxide thickness variation. Similarly, Yeah, the second parameter is the random dopant fluctuations. Any questions? If you have any questions, you can ask. You are sleeping, right? How many of you are sleeping? Please raise your hand. He is raising half, partially. Okay. No, I just wanted to make it light. Don't worry. Okay. Huh? Yes. So everything is VLSI only, right? So we are teaching VLSI only. And you are yes, of course. Everyone should understand because I'm expecting all are from electrical, electronics, and computer sciences. So they must be knowing these things very well. Okay. Perfect. So the second parameter I was talking about is the random dopant fluctuations. What happens with it? Can anyone explain what happens with the random dopant fluctuations? So ultimately, for the diffusing the things, you must dope something, right? Some impurity is required. Okay. So with the newer technology, the number of dopants are keep on reducing. Okay. So number of dopants are keep on reducing. What it means? Let us assume in the older technology, I'm giving the similar kind of the numerical understanding so that you can understand what is happening. Let us assume in old technology, there was 1,000 dopants. I'm just giving a rough number, just to understand. There are 1,000 dopants per unit area. Okay. But to attain the similar kind of performance, in the newer technology, the number of dopants will reduce. Let us assume it becomes 500. Okay. Now, I am saying the same because it is not possible that you can say, okay, there is no counter like how many dopants you are adding into the material, right? So there must be some variations. If you are saying 100 and for 1,000 dopants, you have to process that for, let us say, 1 second. But maybe in 1 second, there could be 950 or there could be 1,010. That's possible. Exact 1,000 dopants may not be possible, and this is completely impossible. Okay. Now I'm saying, what number I'm saying? Let us assume in the old technology, I need 1,000 dopant per unit area, and there is a variation of 50 dopants, like 950 to 1,050. So this is what you can calculate, like this is around 5% of that. Now, let us consider the new technology where I need number of dopants like 200, and still the variation is remains same like 50. So that will become 150 to 250. So the percentage of variation is remain like high. So this is what we can call them the random dopant fluctuation. And this is why happening because at the newer technology, the number of dopants should be reduced. And if they are reducing, and if even you have the same number of variation, the impact will remain same. Impact will be higher at the lower technology. Okay. So this is what we can call them the random dopant fluctuation. And third and very important parameter is the line edge roughness and line width roughness. Okay. So what this LER and LWR is. In the lithography process, what happens? At the older technologies, I think you must be using some 130 nanometer wavelength of light for the lithography process. Is still and for the lower technology, is still a similar kind of wavelength of light is being used for the lithography process. If the same wavelength of light is being used, yeah, there is other process as well so that you can get the lower technology, but the same wavelength of light is being used. So what happens more than that, if you are fabricating the older technologies like older devices, large devices, long channel devices, then might be the same wavelength of light is being used and you can properly get the devices. But at the newer technologies, you cannot get the same pattern like what you was expecting because of the difference in the wavelength of light in the technology node which you want to fabricate. Okay. So because of that, you was expecting like your device should be like this one, but there could be some variation in the line, there could be some variation in the width and all those things. So this can create the variations, process variations. This is what we can call them the process variations. They are changing the performances of the devices after fabrication. At the time of simulation, I was expecting my device should look like this one. But after fabrications, I don't know whether my thickness will reduce or my edge will reduce or edge will be rough. Based on that, your performance will be changed. And if the performance is changing, what it means, this is creating a question mark on the reliability of that circuit. So you must have a window, how much variations I can tolerate at the, for the fabrication or for the, like if you have some range of variation that you can accept it, and after fabrication, if that variation is within your window, then it's fine, otherwise you have to redesign it. Okay, so this is what we can call them the line edge and line width roughness. Okay. Yeah, so similarly, yeah, this is very important diagram here to understand the supply variations. Now we know that, I think I have already taught this in the course, like BTech, like MTech student must be knowing these things. They all must be knowing these things. We know that the dynamic power of any circuit is directly proportional to the square of the supply voltage. Okay. So if I want to make a low power circuit, so there are two ways to do that. What are the way? The first way is change the topology or change the supply voltage. If I don't want to change the topology, one of the way is to reduce the supply voltage, so directly that will impact on the power dissipation. Is it clear or not? Okay, so I know that alpha FCV square is the formula for dynamic power dissipation. So if I will reduce the VDD, definitely my dynamic power dissipation is going to reduce. Okay, so if I see this diagram, what this diagram says, that impacts on the delay. The delay relation is given in the such a way, like if we have a high VDD, delay will be less, and the vice versa is the case. Now, I was giving some number about the, उनको लगे कहाँ से बोल रहे हैं, है ना? दिख रहा है कैमरे में? नहीं. Am I visible? I am not visible. I should switch here, right? Okay. Huh? Where I am? I don't know. Okay, fine. No, they should know from where he's speaking. Otherwise, they will tell, okay, they have run the recording and they are enjoying from background. Huh? Yeah, I think same lecture you can find on YouTube, right? So this is available actually. Fine. So I was talking about this supply voltage. If I have a higher supply voltage, definitely the delay will be less and the power will be higher, and the vice versa is the case. But if I want to understand something like, because let us assume if I want to get less power dissipation, in that case, I have to reduce some supply voltage. But I know that if I will reduce the supply voltage, that will impact on the delay, means delay will be higher. Okay, so now let us try to understand. I have some boundary, I have some range for the delay, and based on that, I have decided a particular supply voltage. Let us assume. Let us assume I have decided this particular supply voltage. Let us assume something close to this one. And I am assuming that at this point or at this VDD, I am getting very good, because the green line says that if my delay is more than that, it is unacceptable. Below that, it is acceptable. Similarly, this and this particular delay can be achieved at this particular supply voltage, whatever the red line is crossing here. So if I am keeping my supply voltage somewhere here, might be my delay will be lower than whatever the critical value is. Okay, so I am getting the good, like the delay within the range, and also the supply voltage is lower so that I can save the power. So I have some trade-off between these two. Now there is one catch here. What is the catch? Let us assume supply voltage is fluctuating. Okay, and if I have kept my VDD at somewhere here at this point, and let us assume my supply voltage is varying by 10%, plus minus 10% variation is there. So what can happen? If it is increasing, there is no problem. There is no problem because my delay is within the boundary. But if my original supply voltage was somewhere here, and now it has been reduced by this factor and it has crossed this value, so my delay will be higher, your system can fail because it has more delay than expected one. So this is really very important. We need to be careful about selecting the supply voltage. Only the power is not the constraint. The delay is also very important, and that need to be seen like overall system delay. What is the overall system delay? And accordingly, you can decide what should be your supply voltage so that you can maintain the stability against the supply variation, as well as the in terms of power and in terms of delay, both. So that's really very important. Okay, so so this is what we can call them the delay. Similarly, yes, one more thing is really very important. This graph is a little bit interesting. How this is interesting? Let us try to see. Okay, So I know that if I have a chip, and in that chip there could be multiple modules, n number of modules could be there. How many and I know that it is not necessary that how many modules I have, all the modules will have an equal activity factor. Is it true? Is it possible that I can maintain the same activity factor for all the modules? No, that is not true. Some of the modules may have the higher activity factor than others. Okay, if the activity factor is different, what it means? There is maybe more toggling, more switching is there, more switching power dissipation will be there. So there may be hot spot can be created, and some region where the activity factor is more will have more heat than the other one. That's possible, right? So this is what we can call them the variation, temperature variation. The effect of temperature variation could be different. That depends on what is the activity factor, and accordingly the performance of a particular model will be different than the other one. Might be the deviation or the change in the performance of the module where the hot spot has been created will be more than where there is less hot spot. So that's also, so this is what we can call the temperature variation. The range of variation could be possible because of this hot spot and all those things. Okay, so we need to understand, like, so the proper designing of your SOC is very important. You have to place them in such a way that the activity factor should be scattered, or they should be similar kind of, so that this kind of variation can be avoided. Is it clear? Okay, so this is what, yeah, so this is if you have the more workload, definitely more switching power, switching activities, high power dissipation, more heat will be generated, temperature will be increased of a particular region. Okay, and that's a problem. Okay, so this kind of things we can call them the temperature variations. Okay, it could be local, it could be global. Okay, fine. Yeah, so this is not important. Yeah, this is saying like how higher supply variation, process variation, and temperature variation impact on the delay. That's fine. Yeah, I think BTI I have already discussed in the last lecture, so I'm skipping these things. But let me give you the brief idea. I think let me recall it. Let me tell you what these BTIs are. Generally, they are one kind of temporal degradations. Okay, and because of that, there are some of the impacts like maybe here is the output. Yeah, this one. So these are some of the impacts like degradation in the drain current and delay and the threshold voltages. Okay, and because of that, if you see this diagram, what this diagram says that if this one was your actual design at the time, but because of the effect of NBTI, might be your lifetime can be reduced. Okay, lifetime can be reduced because of the NBTI effects. So this gives you the information about what could be the lifetime. So this is what you are claiming, like this should be the lifetime of circuit, but because of the NBTI effects, they are impacting the performances and might be lifetime will be reduced. Okay, yeah, this is what about current, leave it. Yes, second reliability concern is the hot carrier injection. What is this hot carrier injection? Hot carrier injection is basically what happens, like the charge carriers get accelerated and they attain sufficient kinetic energy, and they can inject, instead of moving from here to here, they can inject, they can penetrate into the oxide. Okay, so this is because of the attaining high kinetic energy by charge particle which we are using for in the device. Okay, and because of that, what happens ultimately, the result is they are increasing the threshold voltage of the device, and if they're increasing the threshold of the device, definitely performance will reduce. So the SCI is a second kind of reliability concern, or another kind of the temporal reliability concern, where they are impacting on the threshold voltage because of the injection of charge particle into the oxide because of getting high kinetic energy, and the impact is remains same, like they reduce, they increase the threshold voltage and the current drivability reduces. Yeah.
The increase or decrease in the threshold will depend also on the what
Many.
polarity of the.
Yeah, of course. That also depends. So generally this SCI happens during the transition, like from 0 to 1, 1 to 0 transitions. And the NBTI happens at the level during the stress and recovery. So this is what you can say, like if I have a pulse train, so during logic low, logic 0, NBTI will happen, and during transition SCI is possible because they are getting more accelerated in this range. Okay, so this is one of the reasons. So this is the SCI. Third and very important parameter, like one of the temporal degradation is the time-dependent dielectric breakdown. This time-dependent dielectric breakdown means, like, see, we know that we have studied the dielectric breakdown or dielectric constant of any material. Okay. Sorry. Temporal degradation means the degradation with respect to time. Time-dependent degradations. Okay. So that's we can call them the temporal degradations. Like NBTI, SCI, and TDDB are the temporal degradations. Okay. So the time-dependent dielectric breakdown, if we talk about what this TDDB is, basically we know that whatever the dielectric material we are using, they have some dielectric constant. Okay. If they have some dielectric constant, what does it mean? It means that they can sustain up to certain electric field. If you are keep on increasing the electric field across them, might be they can lose its dielectric property. Okay, if they can lose its dielectric property, might be your dielectric will start behaving like a conductor. That's possibility. Okay, so what happens if there is some defect at the time of yeah, so let us assume initially I have something like this, and there is some defect in the oxide. Okay, and with the time, what happens? There is more defect generated, and if more defects are generating with respect to time, they can create a leaky path, because this is the polysilicon, which is like a gate. This is the silicon substrate, which is the normal bulk one. Okay, and if somehow they can create a leaky path, if there are more number of defects, and then they can create a leaky path between the polysilicon and the silicon, so they will start flowing one current, and it will lose its dielectric property. So this dielectric, so these defects generated with respect to time, more generation will be if you are keep on operating for longer. Okay, so this TDDB is one kind of defect that happens in the oxide, and if the leaky path started, like if the current started flowing through this path, like leaky path, then that will break down your device. Device is not going to work because there is a short circuited. Okay, so there is no dielectric now. Okay, so if that happens, it means that breakdown will happen. So this kind of phenomena, we can call them the time-dependent dielectric breakdown, because the dielectric material loses its property. Previously, it was dielectric. Now it is started conducting the things. So this is what we can call them the time-dependent dielectric.
So can we say when the charges get trapped in the oxide due to the hot carrier injection, they can also lead
yes,
to this?
Yes, of course, absolutely correct. So they can lead to create a leaky path between these two.
Why are we calling it as a hard breakdown?
Hard breakdowns, yes, very good question. So I was expecting someone should ask. Okay, that is why I did not explain it. Okay, so there are two kind of breakdowns. So one breakdown which I just discussed, this is what we can call a soft breakdown, which is because of the defects in the dielectric material. Okay, hard breakdown means if you are intentionally increasing the electric field across the dielectric material, and it will start losing its property. So that is like forcefully I'm started conducting the, like I'm changing the property of that dielectric material. So this is because of the high electric field. So that is what we can call them the. So let us assume if I can sustain up to certain range of electric field, if you'll increase the electric field, definitely I will lose my property. Okay, so this is what we can call them the hard breakdown. Fine. So this is the TDB. So if I try to embed all this, so as of now, what we have studied some process variations. That was the global and the local process variations. And then we talked about some temporal degradations like NBTI, PBTI, SCI, TDDB. And then we also talked about supply and temperature variations. But it's very, yes, please. No. TDB, because they will create a leaky path there due to defects in the dielectric material. Once defect is generated, you cannot remove it. So that's one kind of problem. So this also defines the lifetime of your transistor. Okay. So this is possibly, so see, it can be discussed in more detail. So let me explain in another way. So both is possible. Why I'm saying, because if you see the NBTI, if you see the what is happening with the NBTI, like if the transistor is under stress, they tunnel into that and they trap into the oxide. And if that happens, they will create a leaky path. But when the transistor will move into the recovery phase, might be some of the charge tray will come out, and it might be that device will start working like a simple one. But with the time, because there may be some permanent trap, after some time they will break down. So that may happen. So this is possible. Like there must be some recovery, and because of that, it can be recovered back. But once the permanent shift is more than the required one, it will break down the device. Okay. So if you try to embed all these things, this is really very important diagram actually. I told you about the, I have 30 minutes time. And how many slides? I'm fast today actually. Generally, I used to take 10 slides in 1 hour. Okay, so but it is more than that. And it is because I'm giving the expert talk. Right? In lectures, it's less than that. Even 5-6 slides, huh? Per lecture, 6 slides, not more than that. Sometimes only 1 slide, huh? That depends, like what I'm trying to explain and how much you are able to understand. That also matters a lot. If everyone is understanding, I can move 50 slides in an hour, right? But I don't know how much you can capture it. Perfect. So let us try to understand what is happening here. So I was talking about the process variations. Process variation, ultimately, the Monte Carlo is one of the way to understand the variability issues. Okay. So let us assume, I know that if I'm applying a Monte Carlo simulations due to these process coordinates, like to understand the process variability, okay, process variations, then might be, let us assume the distribution of delay is something like this one. What does it mean? It means that the mean value of your delay is somewhere here. T is equal to 0 indicates like it's time 0. I'm not considering the temporal degradation here. Okay, so the mean value of your delay is somewhere here. Okay, and there is some scattering because of the threshold voltage variation, and delay Monte Carlo or delay distribution will be something like a histogram, like this one Gaussian distribution. Okay, now let us go back to the NBTI and the PBDI concept. NBTI concept, let us say. What NBTI says? NBTI says that with respect to time, your threshold voltage used to shift. That increases. Okay. Now let us assume. Let me tell one thing here. To write it. Okay, here it is. But it will be permanently in. Okay, let's try to understand what is happening here. No. I don't leave it. So otherwise, my time will be wasted. So let me explain on the board. There. I don't know whether you are able to see or not. So let us assume I have a histogram, something like, I have a. So let us assume this was the delay, and my Gaussian distribution is something like this one. Okay. Now I understand that. Okay. This is the mean value of your delay. Okay. Mu of delay, and you know that, let us assume this is the minimum delay that I can accept, and this is the maximum delay which I can accept. Okay, and beyond that, if my distribution is something like this, might be some of the sample may get failed. Okay, so what I need, let us assume this is the minimum delay that I can accept. This is the maximum delay which I can accept. Okay, and if delay is in between these two, it means that your circuit is working properly. So if my distribution is something like this, there could be one more possibility. Let me use a different color, okay, so that you can understand. So let us assume if my distribution is like this, there may be possible, like if more process variation, my distribution could be something like this. There could be a chance like my distribution will be something like, yeah, ultimately height will change. So ultimately I'm not taking care of that thing. Let us assume I have one more distribution, and that is something like this one. Okay, and one more thing like which I have made over here. Let us assume this is at the boundary. So the minimum one which I have got it like this one. So now let us try to compare what I have explained. What this blue curve says. Blue curve says that even after applying the complete process variations, the distribution is within the window which I was expecting, minimum and maximum delay. So even though I will have some process variations, definitely my system is going to work properly. If you see the second diagram, which was the yellow color, they are at the boundary. Okay, so they are at the critical case. Okay, so still my system will work properly. But if you see the next one, which is in the green color, what this says, there are some range where I will get a proper delay responses, which is my boundary. Left side does not matter. Right is less delay is fine, no problem. But if you see the right side one, the delay on right side is higher than whatever limit you have. And for those ranges, your system will fail. They will not work because they are not meeting your specifications. Okay, so what you need less process variations. Okay, now let me extend the same analysis. What we saw here in the yellow color, we saw we are at the boundary, and for all the samples, my delay is within the range. Now add the impact of this one. What is happening here? After adding the impact of NBTI, your threshold voltage is going to increase. That is impacting on the delay, means delay is going to increase. If the delay is going to increase, means your mean value has been shifted to the right direction. If the mean value has been shifted to the right direction, what it means? Your curve, which was this one, I am extending this yellow one. Okay, this may be shifted somewhere here. So on left is perfectly fine, but on right side, previously it was like a reliable one. Now after NBTI, it may become the unreliable. Understood or not? Okay, so this is the range, like some of the sample may get failed after adding the impact of BTI or temporal degradations. So temporal degradations play a major role on deciding what is the range of your process variations. So if range is less, definitely even after the impact of NBTI, that will be within the window. But if it is at the boundary, it may fail after a certain period of time. Some of the sample may get failed after a certain period of time. So that matters a lot, and this diagram is really very important. Any question at this point? I don't know online candidates have seen it or not, I don't know. But maybe you can capture this, send to there what I was explaining. No. Supply variation is a different thing. Process variation at the time of fabrication, how your device is being fabricated. And that depends on many things, like how well oxidation you have done, masking, etching, and there are many parameters that decides. That's complete the flow of fabrication flow that decides the variation. If you have optimized your complete flow properly, there will be less variation. Otherwise, there will be high variation.
The processor companies who designs the process, when they want to close out the tape out, basically they don't only have to perform the Monte Carlo on the just like this, but they also have to include the effects of this NBTI. And
yes, they need to test it. So if they know that there is a, even let us assume what happens. if I have set a boundary for the delay, okay, and I am performing the Monte Carlo simulation, and I know that after 5 years, my threshold voltage is going to increase by 10, let us say 10 millivolt, okay. And if I will add 10 millivolt delay threshold voltage, then how that is going to impact on the delay and how much variation I will get. If this is within the window, then they can say. So they have to give some guard banding that is required. If they have given some guard band, definitely even after 5 years, your system is going to work. But before that, this is fine, perfectly fine. So that guard banding is required. You should not expect your behavior should be like yellow. It should be like a blue one. Blue one is expected, so that even though after variation, you will have some range that can be adjusted later on. Okay, so I was talking, yes. Yes, very good question. I think yesterday I was talking about the effect of NBTI is more if you have more negative VGS. So at lower supply voltage, the effect of NBTI will be less. Then your lifetime will be better. But again, the problem is lower supply voltage will lead to the higher delay, so performance will be slower. So there are always a trade-off between all these parameters. Yes. Yeah, there are different mechanism scheme. Like you can, for that, just read one of my transaction paper. There I have mitigated the impact of NBTI after designing the circuit. So body biasing could be one of the techniques that can help us to, because body biasing help us to change the threshold voltage. And if the threshold voltage is increasing, and if you apply the reverse body voltage, definitely that will compensate that change. Yes, some block that will change the body voltage with the time, like with the different values, and that will compensate in the same work I have done in my one of the work. So you can Google it and you will check it. Okay, fine. So this is the NBTI effects and like reliability concern and their impact. Okay, fine. What happened? Not working? Okay. Oh, okay. Yeah, no, it's fine. Perfect. So here is the combined effect of everything. Let's see what this graph says. I don't have too much in writing. I have everything in picture form, right? Okay. So let us assume I have this NBTI, PBTI, SCI, all these effects. They are basically at the material level, like SiO2 and silicon and all those things. So all these effects are observed at the material level, but their impact at different abstraction level could be different. Let us say if I have this impact, if you're talking about a simple device level like a transistor, the impact of NBTI will be observed like in terms of the threshold voltage variation, current variation, transconductance variation. So all these parameters will be observed and they will define like how much change is there in these parameters because of the NBTI. So NBTI is happening at the material level, but their impact at the device level will be like in terms of VTS, in terms of current, in terms of transconductance or on the other parameters. Whereas if you are using the same device where the impact of NBTI is more in the circuits, like inverter, I have to observe the impact of this VTS in terms of delay or in terms of power. So even though the variation is same, but the impact or the parameter which we are going to observe at the different abstraction level will be different. So at device level, we have to observe the VTS variation. At the circuit level, we will observe the impact on the delay and the power variation. Similarly, if you talk about bigger circuit level, the noise margin is going to be impacted because of this variation in the threshold voltage. We have already studied in the classroom, right? So what happens, like if there's the impact of NBTI, PBTI or anything else, definitely at the circuit level like memory, we have to observe how it is impacting in the noise margin which we have designed. Similarly, at the system level, timing violation kind of things is important, because I was talking about this one. If one of the procedures is in there, if they fail, definitely they will violate the timing and might be your whole the complete system. So timing violation, data corruption, this could be possible at the system level. So ultimately, at the lower level, like lower abstraction level, the impact is NBTI, but other abstraction level, their impact can be measured in terms of other parameters or different parameters. Okay? How many of you are sleeping now? We need to keep transistors in sleep mode as well, right? Fine. So that we can avoid these effects. Perfect. Okay. So we understood, like, if I have some variability, how these variabilities are impacting at different abstraction level, and we understood these things. Now let us try to move ahead again. Yeah, this is one of the bathtub curve. It's not bathtub where you have to bath, okay? But this explain us the probability of failure at different lifetime of the chip, okay? At different lifetime of the chip, like when we fabricated, the initial defects could be like early failure, infant mortality, defect burn-in mortality. So there is a possibility that more failure rate could be at the initial level, but once you have started using the chip, might be the rate will be higher. So let us assume I have fabricated 100 chips. There is a possibility like suddenly 10 chips are not working. So there is a high possibility like infant mortality is very high at the initial level. Once your chip started working, then infant mortality is not a big problem. Then other kind of failure comes into the picture. Okay, so this is how the failure rate is keep on reducing with respect to time. But this is really very important. After a certain period of time, they started wearing out. Okay, so wear out, because of the wearing out, failure probability increases. Because of early failure is high, but with the time, early failure, like this kind of failure will be less. But if you see, the combinedly, their impact is something like a bathtub. But one more thing that you have to understand what is happening here. One thing is important, like if you change the technology, so with the lower technology, the probability of failure will be higher. Okay, this is for older technology, this is for bit lower, newer technology, this is for newer technology. So this probability keep on increasing if you evaluate, like your transistor is evaluated, like more recent technology you have used. So this bathtub indicates that the relation between the infant mortality, wear out failure, and the impact of the technology or different technology nodes, and how it can be related with the overall failure probability or failure rate. Okay, so this is really very important. This particular bathtub curve is true for any kind of thing, even mechanical system. In the mechanical system, this bathtub can be applied. So there is a high. So they are using to test their reliability. Okay. So now you can see here the window of lifetime is going to be reduced if your technology is sinking down. So initially I have a large window here. Here the window is very less. Okay. So advancement is important, but not in terms of lifetime. Okay. So you have to maintain that lifetime as well with the advancement. Okay. Now the second thing is the soft error. So how many you want to continue the things? Huh? Sleeping? How many of sleeping? Huh? Not sleeping? Okay, so let us have a chit chat. Like, if you have any questions till now, you can ask the questions. Then we can. Yeah.
One question.
Yeah, please.
So if I want to design any processor for space application, like maybe it is taking data from a lot of sensors and you want to process. So does it mean that even though I can design a processor at 3 or 4 nanometer technology, but that space application has to survive at least for 10-15 years, I should not design the processor at 3 or 5 nanometer. I should move to 28 nanometer or something so that it can sustain for a long amount of time.
Yes, that's true. But that you have to see like how much performance you need. If you are able to maintain the performance what you need with the older technology, then it is always recommended to use that. So that matters a lot.
Because when they sent Chandrayaan, they had used their in-house 180 nanometer.
Yeah, some of the chips they have used, not too many, but some of the chips they have used there. But majorly they have used at the base station, not at the in the space. So most of the chips which the SCL has fabricated, some of the chips they were using in the satellite But most of the chip they use because they are not trusting themselves only. So at the base, there is no problem like high energy particle. So at base station like network unit and here and there, they used to use it, but not in the satellites. So that's also one of the challenge because of course, you can design it, you can test at the local level, but once the satellite is launched, it's cost a lot. Once your one model is failed, you can destroy everything. And then more pressure comes towards the SCL, like this is because of you, this is destroyed. Okay, that's the problem. Okay, so let me take a sip of water, then we'll continue. It's fast, sir? It's fine. Fine. Okay. Yes, please go ahead. So now is Ujjwal is interested in reliability. Okay, please go ahead. Sorry, say again. Yes, so high K generally, why we need high K? High K generally, see, if I'm using the low K, to get the same dielectric constant, the thickness will be less. High K help us to get the equivalent dielectric constant with more thickness. Okay, so if you have more thickness, there is a more scope to collect the defects, and might be TDD will be less in the high K as compared to low K because the thickness is very less in the low K and for the same constant I'm talking about. If I'm saying the same constant, it means your thickness will be different in both the materials. So high K will be better in terms of TDD. Yes, yes, yes. So yes.
Sir, this recovery is a factor of the clock cycle.
Yes, activity like duty cycle is important parameter. Like at which rate you are changing your logics from 0 to 1 and 1 to 0.
So at the system level also they can address some of these issues, right?
Yes, so by properly optimizing your activity factors, definitely if you are not